Okay, hello everybody. So we have another exercise here to practice perturbation methods applied to the solution of algebraic equations. This example here has been taken from tests that I organized in the framework of my course on perturbation methods at the University of Liège. And it aims at solving a problem which is that equation. So at the same time, if you guys who are listening are one of my students and want to get ready for the test, this is exactly how it looks like. So you see, for this kind of test, you have 1.5 hours to solve that problem, which doesn't seem to be too constraining. We'll see this in a few minutes. And this is how this is stated. So let's consider the equation. We know that epsilon is a small number. We know that alpha is a strictly positive number. Okay, read carefully the statement. That is always very important. Then first we ask you to discuss the unperturbed problem and its solution. Then we need to find a 3-term expansion for all 3 roots. We have 3 roots because this is a 3rd degree polynomial here. And we are going to restrict this to the case where alpha is of order 1. Then it's asked to discuss as a function of alpha. So it means that now alpha is not necessarily of order 1 any longer. It can have other orders of magnitude. We want to discuss the orders of magnitude of the 3 roots of that equation. So in fact, it just comes down to find the order of the magnitude of the roots, right? Something we used to do. And then question 4, we'll touch it a little bit later. So I suggest we first start by solving the first 3 questions. We'll come back to the statement a little bit later. All right, so 1 is very easy, unperturbed problem. Okay, this is every time where we need to start. You just replace epsilon by 0. Beautiful. The left-hand side is equal to 0. Beautiful or not, I don't know. But you see that the unperturbed problem actually 0 is equal to alpha. And alpha is a strictly positive number. Okay, what does it mean? It means that there is no solution in the unperturbed. And so it means that all 3 roots just appear because of the small number epsilon in that equation. Okay, that's it, right? Discuss the unperturbed problem and its solution, all right? So this is very easy. There's nothing else we can say here. Second, find a 3-term expansion for all 3 roots of that equation. So we just know here at this point that we should expect 3 large roots. By the way, is the problem a regular problem or a singular problem? This is, of course, take a second to think about it. Regular or singular? This is, of course, a singular problem because we start from a 3rd degree polynomial here, and it becomes a 0th degree polynomial over there, even if, and even all the more, it has no solution here. So it means that this is a singular problem, and even more, all 3 roots are singular. All right, so we should expect 3 large roots, meaning that none of these roots can be captured starting from the original problem with a regular ansatz. We need rescaling. We need a rescaling. Or in other words, what are the orders of magnitude of the large roots? All right, so at this point we know they are large, but we don't know whether they behave like 1 over epsilon, 1 over epsilon square, or 1 over square root epsilon, or whatever. All right, that's something we need to determine. And so to do this, we have this method called the pairwise comparison. Pairwise comparison, which says, consider any possible combination of 2 terms among 4. and assume that two of those four terms, they lead, are much larger than the other remaining terms. And let's also assume that they have the same order of magnitude. Okay, for instance, assume the first two terms, just to start with something simple. We did this in previous exercises and it seemed to work. And let's just replicate this over here. Let's assume epsilon x to the third has the same order of magnitude as epsilon square x squared, and they lead, meaning that they are larger than remaining terms. So epsilon to the third x and alpha. All right, so if we translate this into the order of magnitude of epsilon, we see that we can simplify this expression here. Just simplify out left and right by epsilon and also by x squared. So we see that if we assume that these two terms have the same order of magnitude, it means that x needs to be of order epsilon. And now we need to revise the orders of magnitude of each term, the first term, and just assess the assumption we made, which is, do they really lead? All right, so the first term is something that will be of order epsilon to the 4. That is tiny, but why not? The second term is epsilon square x squared. This is epsilon to the 4. Okay, of course, this is expected that these two correspond to each other because we precisely chose this quantity in order to make sure these first two terms have the same order of magnitude. We need now to investigate a little bit more and see what's going to be the order of magnitude for the other remaining terms. We have epsilon to the third times x, and this one will be also epsilon to the power 4. That's an interesting point. That's something we've never encountered so far. Is it a problem or not? No, that's not a problem so far, because it just says that in the leading, actually the balance will be occupied not by just two terms, by three terms. It's not a problem at all. We need to have at least two terms balancing each other in the leading balance, and we found in this place a third term, which is probably not so much of an issue. All right, but what we need to make sure is also that these are much larger than the last term, and the last term on the right hand side, this is alpha, and this is epsilon to the power 0 because this is 1. And what we see, in fact, we see that T1, T2, T3 are much smaller than T4, which means that the leading term is not T1, T2, but the leading term is T4. All right, so it means that the assumption that we made earlier is a wrong assumption. All right, so it means that the balance is obtained by balancing something different. Another pair, and we can try other combinations and probably try them all, or we could use this general method, a general approach or method. It doesn't really have a name. That's something I have designed. I just realized that over the years the students like to have something systematic to work with, and I just designed this method. I don't know whether this is really useful or not, but I guess it helps understanding a little bit how the different orders of magnitude of the different terms can combine or balance each other. And how does it work? We just say, remember what we did earlier. We just have to say that x has order of magnitude epsilon to the power q. We need to rewrite the orders of magnitude of each term. All right, so we make it in fact general. This is the general approach. So we do the same as what we did, except that now x is epsilon to the power q, meaning that epsilon times x to the third is epsilon to the power 3q plus 1. Second term is epsilon square x squared, which means epsilon to the power 2q plus 2. Third is epsilon to the third times x, which is epsilon to the power q plus 3. and T4 is alpha, which is 1, or order 1, so which means epsilon to the power 0. All right, so let me just denote by the exponent here, the values that we give to T1, T2, T3, T4. All right, so we have 4 different values. Okay, and so what we do next is that we just plot these 4 values. I'll try to do this as precisely as I can. We need to draw them as a function of q. Remember, we use reverse axis here because we are interested in small values of x, because the exponent of epsilon is large, and on the right we have large roots, large values of x. All right, so starting, for instance, with the term number 4, we see that term number 4 is here, T4, because the exponent is always equal to 0. Then let me just go probably reverse. T3, when q is equal to 1, one, 2, 3, and 4 passes through that point, and when q is equal to 0, passes through this point. When q is equal to 0, T3 is equal to 3. All right. So this is what we have. This is what we have for T3. Okay, so that's the order of magnitude of the third term. Then let's do the same for the second term. Q plus 3. Second term, 2q plus 2. So when q is equal to 0, the order of magnitude of that term is epsilon square. And when q is equal to 1, we have a 4. So that's something that looks like this. And this is T2, 2q plus 2. Last but not least, when the first term, 3q plus 1, when q is equal to 0, passes through this point. And when q is equal to 1, we have 4. So it passes again through the same point as earlier, like this. We have T1, 3q plus 1. All right, so it means that the leading order term is the one that is the largest. So for a given value of x, for instance, over here, small value of the root, we can look at the orders of magnitude of the different terms. And what we see that term number 4 is over here, is large, much larger than T3, which is itself much larger than T1, T2, and then itself much larger than T1. All right, so there is no balance here. The first point, or the first place where we can find a balance between two terms is exactly at this point. All right, where we have a balance between T1 and T4. Okay, that's the intersection of the line corresponding to T1 and the line corresponding to T4. And if we keep increasing the order of magnitude of x, what we have is that the largest term is the term T1. And so you see that never ever T2 or T3 might be the leading terms. All right, so that's a simple problem, That's a problem where we have several terms, 4 of them, but you see that in this problem, it could be any physical problem, you see that the problem is just governed by only 2 of them, T1 and T4. And so to find the right scaling for the root, now we just have to write order of magnitude of T1 and T4 are the same. This is in fact a combination that we should have chosen in the pairwise comparison in order to make things work properly. And to write this, we're just going to say that 3q plus 1, 3q plus 1, that's T1, is equal to 0, meaning that q is equal to minus 1 over 3. Minus 1 over 3. And so this is, it means that the root is a large root, so the large root, and that's the only option. So it means that all three roots have the same order of magnitude. The large roots have order of magnitude epsilon to the power minus 1/3. And this is indeed something large. So you see, earlier we said, okay, we know that the roots are large, but we don't know the order of magnitude of those roots. We don't know whether this is 1 over epsilon, 1 over epsilon square, and so on. This is none of them. This is in fact 1 over cubic root of epsilon. And this is how large they are. Okay, so this is interesting to know, because if you were using a numerical technique in order to solve a problem like this, of course this one is probably too simple, but you see we will apply the same techniques in a more complicated context later, even for partial differential equations. You know exactly where to look for the solution. And so once we know the order of magnitude of the root, we can rescale the problem, rescaling. And to rescale the problem, what we can say is that x is epsilon to the power minus 1/3 times x tilde, with this new coordinate being of order 1, and of course different from 0, otherwise that wouldn't be a rescaling. All right, what we need to do now is to substitute this in the governing equation. And so the governing equation, let me just copy it so that we can keep it with us. Here, okay, we need to substitute this in the governing equation. So we have first term epsilon multiplied by x to the third, so that x minus 1 multiplied by x tilde to the third, epsilon square, epsilon minus 2/3 x tilde square, epsilon to the third, times epsilon minus 1/3 x tilde is equal to alpha. And you see that these two, they disappear, and the leading order term, they are of order 1. All right, so meaning that we don't have to multiply or divide the governing equation by any power of epsilon, because this is already of order 1. And so what we have here is now epsilon to the power 6 minus 2, so that's 4. 4 over 3, that's indeed a small number, plus 9 minus 1, 8 thirds x tilde. All right, we see that we can make it simple and redefine this as a new quantity, which is also a small quantity, like this, meaning that this is equal to this new epsilon square. All right, once this is done, we can use a regular ansatz in epsilon. So of course I will use the sequence 1, this new epsilon, epsilon square, and so on. Just to start with, hoping that it's gonna work. Well, it should, because the problem is fully regular in this case, so there shouldn't be any big problem to expect. So this is the thing you should start with, and if it doesn't work, then you need to seek for another sequence. All right, but and the way to seek sequences is something we've discussed already, and hopefully we won't have to apply this in this problem. All right, so it means that we use x tilde is equal to x0 plus epsilon x1 plus epsilon square x2, and so on. I will just stop here because we need three terms, three-term expansions. So we need now to substitute this in the governing equation. X tilde to the third. Let's probably just compute this one because it's going to be a little bit more difficult, I guess. That's x tilde to the third plus. You need to remember here the binomial theorem probably. So we have 3x0 because we have three ways to combine x0 and x1 together with epsilon in order to get a power in epsilon, and then we need epsilon square. It's going to be the same, 3x0 and x1 square. And there should also be 3x0 for the same reason as what we had before, x2 and epsilon square. And then plus terms which are of order epsilon to the third. We can also, just to make sure we don't mix it up, let's try to do the same with x squared. We have x tilde squared plus terms in epsilon, 2x0, x1. Terms in epsilon square, we have x1 square plus a double product here plus terms in epsilon to the third. All right, so this is something I just wrote momentarily in order just to help substitution in the governing equation. So let's push this in the governing equation and keep terms until probably order 3. Oh, which is, in fact, is not so difficult, right? Because we notice here that the highest power x to the third. Oh no, sorry. We should start from that equation here. So let me just make sure to avoid any problem. Let me just rewrite it. So the governing equation that we want to solve is x tilde to the third plus this new epsilon, x tilde squared plus epsilon squared, x tilde is equal to alpha. All right. So what we need to do is just copy paste what we have for x tilde to the third. All right, so x0 tilde to the third plus 3 x0 squared x1 tilde times epsilon plus we have 3 x0 x1 square 3 x0 square x2 times epsilon square. Okay, that's for the first term. Then plus epsilon times x tilde, meaning that we are going to have plus x0 square times epsilon. Sorry, coming from there. x0 square times epsilon plus twice x0 x1 times epsilon square. All right, so that's for the second term, and then the last term plus epsilon square multiplied by x tilde, which is just x0 in this case after having injected the ansatz, and this is equal to alpha. So now we can write the problem at the different orders of magnitude. At the leading order, we see that we have x0 to the third is equal to alpha, which is a positive number. All right, so that's an equation that has, of course, 3 roots. That's the 3 roots we were looking for. So meaning that x0 tilde is the cubic root of alpha, or the cubic root of alpha multiplied by the exponential of plus or minus 2I pi over 3. All right, so if you want to locate these three roots on the complex unit circle, one is here, one is there, and one is there. All right. Then let's keep going. At the next order, epsilon, this epsilon here, what do we have? We have 3 times x0 tilde square x1 plus x0 tilde square. All right, I just combined here the two terms over here. This needs to be equal to 0. Because x0 tilde is different from 0, we have x1 tilde is equal to minus 1/3. No matter what we have for x0. That's quite interesting. And then if we keep going with the last term, which is a little bit longer, but it should be all right. We have 3 times. Oh, I see that. Look, let's try to use this. What we need to combine is these two terms, this term, and that term, all right? And we see that all of them are multiplied somehow by x0, all right? So I'm gonna just simplify this out. So we have 3x1 squared plus 3x0 x2 plus 2x1 plus 1 is equal to 0. And this means that we have here 1/3 squared multiplied by 3. This is 1/3. And then this is minus 2/3. And this is plus 3/3. So that's 4 minus 2, 2/3. So we have 3 times x0 x2 is equal to minus 2/3. So x2 is equal to minus 2/9 times x0, which means either minus 2/9 square root of alpha or minus 2/9 square root, cubic root, sorry, of alpha times exponential of plus or minus 2I pi over 3. Done. And so once this is written this way, we can just reformulate the problem with the original quantities. And so in particular, just remember that we had introduced this rescaling. So x tilde is just a quantity of our choice. So x is equal to epsilon to the power minus 1/3 times x tilde. So it is equal to it is equal to, or maybe just in between, let me just write x tilde. It's gonna be, let's summarize first. This is x0. So in the first case, cubic root of alpha plus this new epsilon. This is why I should be careful here. This new epsilon here, which we defined over there. All right, I'm gonna get rid of this new epsilon and come back to the previous epsilon, the one that was going in the statement. All right, so if we come back now to the regular ansatz, we have x0 tilde plus this new epsilon times x1 tilde. So it means plus epsilon to the power 4/3 multiplied by x1 tilde, so that's minus 1/3, minus 1/3, and then we have plus epsilon to the power 8/3 multiplied by x2 tilde, which is minus 2/9 multiplied by cubic root of alpha. That's the first root. Let me just write it xa, and the other two roots, xb and xc, will be something very similar. Cubic root of alpha, exponential of plus or minus 2I pi/3, minus 1/3 of epsilon to the power 4/3, and minus 2/9 of epsilon to the power 8/3, multiplied by cubic root of alpha, and the exponential of plus or minus 2I pi/3. Got it? And now we need to return back to x, all right? And to return back to x, we'll consider again the change of variable that we use here, the rescaling that we did. So we need to multiply x tilde by epsilon to the power minus 1/3, all right? So it means that xa is a cubic root of alpha, epsilon to the power minus 1/3, minus 1/3 epsilon to the power 4 minus 1, that's 3/3, so it's power 1, plus, sorry, let me just write it this way, minus 2/9 square root, cubic root of alpha, epsilon to the power 7/3. All right. And what would be the next term? The next term would be 12 minus 1. So it means order epsilon to the power 11/3. And xb and xc follow exactly the same logic. Cubic root of alpha times exponential of plus or minus 2I pi/3, epsilon to the power minus 1/3, minus 1/3 of epsilon, minus 2/9, cubic root of alpha, epsilon to the power 7/3, exponential of plus or minus 2I pi/3, plus order epsilon to the power 11/3. Done. All right, so this is exactly what we were requested. Find a three-term expansion for all three roots of this equation when alpha is something that is of order 1. Okay. Then discuss as a function of alpha the orders of magnitude of the three roots in this equation. All right. So it means that if alpha now is no longer of order 1, it means that the order of magnitude of the different roots can change. And so in order to understand this, I would just suggest we use our brain on this sort of graphic representation. Copy this and paste it over here. All right. That's question 3. So we said before that we have different orders of magnitude for the different terms in that equation, right? And what we used is we use order 1 for the last term, T4, because this is alpha. All right, so T4, this is alpha, and we said it is of order 1 or epsilon to the power 0. So what can we do here in the discussion is just observe what happens if we change the order of magnitude of alpha. And if we change the order of magnitude of alpha, the only place that is affected, those remain unchanged. The only place that is affected is this one. So for instance, if alpha was epsilon to the power -1, something large, we see that we would still have a balance between T4 and T1. All right, so if alpha is such that its order of magnitude is much larger than what we had earlier, nothing changes. All right, so we'll have a balance between T1 and T4. And how long does it hold if we decrease now the value of alpha? This is still the case here, still the case, still the case. It is still the case until this point. All right, so we have a critical place, a critical point over here, which just says that if the order of magnitude, so if alpha is written like epsilon to the power p with p smaller than 4, it means no change. Balance, there is a balance between T1 and T4, meaning that 3q plus 1 is equal to p, and therefore q is equal to p minus 1 over 3. And so the order of magnitude of the root is epsilon to the power p minus 1 over 3, which is in fact epsilon to the power p over 3 multiplied by epsilon to the power minus 1/3, or meaning that x, because epsilon to the power p is alpha, this is alpha to the power 1/3, epsilon to the power minus 1/3. All right, this is what happens if alpha is such that when it's written epsilon to the power p, when p is smaller than 4. What happens now when p is equal to 4? Actually, we see that all terms have the same order of magnitude, and the root, this is just a particular case, right? This is continuous over there. P minus 4, p is equal to 4, so 4 minus 1 over 3. 4 minus 1 over 3, this is equal to epsilon. It means that when alpha, so if alpha has order of magnitude epsilon to the 4, then it means that the root, is x, has order of magnitude x, for x has order of magnitude epsilon. This is exactly actually what we observed when we tried the pairwise comparison first. We saw that if the first two terms balance each other, we saw that they have to have order of magnitude epsilon to the power 4. And in fact, what happens here is that all of them, all 4 terms have the same order of magnitude when x is of order epsilon, and the order of magnitude of all 4 terms is epsilon to the 4. And then if alpha now is epsilon to the p with p larger than 4, what happens if p is larger than 4? We see that the balance does not happen any longer between T1 and T4, but it happens between T4 and T3. There is a balance. There is a balance between the last 2 terms. All right. And so T3 is q plus 3, and alpha is p. So it means that Q is equal to P minus 3. And so the order of magnitude of X is epsilon to the power P minus 3, meaning epsilon to the power P, which is alpha, times epsilon to the power minus 3. Okay, and here we are. That's what we were asked in this second question, right? We need to discuss the order of magnitude of the different roots of that equation as a function of the order of magnitude of alpha. All right, and there is basically no other possibility because as alpha changes, this line T4 travel up and down, and that's the only configurations that we can find. All right, let's just have a quick look at the last question, which could be, in fact, very quick, and which says this. One could expect that alpha does not influence the solution at leading order when it is small enough. That's indeed something we used to have, right? When you want to neglect a small parameter, if there is a small parameter in a problem and you would like to neglect it, it means that you assume that this parameter has no influence any longer on anything at leading order at least, right? And so we would like to do the same here. So how small does alpha have to be to make sure it does not influence the different roots of the problem, right? The question is here, so does such a small value exist? And if yes, how much small does alpha have to be to not influence any of the roots at leading order? All right, so it just means that based on what we did before, we're going to decrease the order of magnitude of alpha, all right, starting from here, and we're going to decrease it and hope that it doesn't play any longer in the balance. But there's no way to do it, of course, right? Because even if we make it as small as what we had in the third case here, you see that alpha still plays in the balance. And so, of course, it's going to affect the order of magnitude of a certain root, because if it is small enough, and small enough meaning that we have p larger than 4, the order of magnitude of the root could be here, or the order of magnitude of the root could be here for a different value of smallness of alpha, all right? And so the answer to question 4 is just simply, one could expect that alpha does not influence the solution at leading order when it is small enough. Does such a small value exist? The answer is just no, all right? So answer to question 4, no, such a small alpha does not exist. All right. So I hope, well, this closes, of course, the solution of that problem. I hope you understood. This is clearly representative of the questions that are asked at a test. So just practice and train with those exercises. I just come up with new questions every year. So there's no need to try to remember any of them. The most important is definitely to understand what you do. And so keep going, guys, and get ready for the next video.